Hello everyone and welcome back to the class. Today in this course of circuit analysis we will study another passive element known as inductor. An inductor is a passive element designed to store energy in its magnetic field, where capacitor was a storage element which used to store energy in its electric field. An inductor is made with a coil of conducting wire, and its numerous applications are in electronic and power systems, and most widely used in power supplies, transformers, radios, TVs, radar, and electric motors. Any element which is conductor of electric current has inductive properties and may be regarded as an inductor. Now, in order to enhance the inductive effect, a practically inductor is usually formed into a cylindrical coil with as many turns of inductive wire as shown in the figure 1. Now look at figure 1. It has a cylindrical object with as many turns of conductive wire. Like capacitors which stores energy, inductors are also capable of storing energy in its magnetic field, and this energy can be used later, and they are also known as storage element. Like capacitors, inductors can also be paired up with resistor to form another class of circuits which have wide applications. And the circuit analysis techniques which were studied earlier are also applicable to inductive circuits. For our voltage current relation, we know that if current is allowed to pass through an inductor, it is found that voltage across inductor is directly proportional to the time rate of change of current, and mathematically expressed in equation 1. And for this directly proportional relation, inductance of inductor will act as a constant of proportionality. From equation 1 we can say that for an inductor to have voltage across its terminal, its current must vary with time, because voltage is directly proportional to the time rate of change of current. Hence voltage across inductor will be 0 if current is constant, or in case of DC sources. From equation 1 we can derive an important property of inductor, which says that inductance is a property whereby an inductor exhibits opposition to the change of current flowing through it. And the unit of inductance is Henry, named in the honor of American inventor Joseph Henry. And also 1 Henry is equal to 1 volt second per ampere. Just like the earlier passive elements like resistor or capacitor, we come to know that resistivity of a resistor or a capacitance of a capacitor both depends on the physical dimension and construction. Likewise, inductance of inductor also depends on the physical dimensions and construction. And mathematically, inductance is given by whole product of number of turns of inductor, area of inductor, permittivity of inductor divided by length of the inductor. If you look at the figure A, where L is the length of inductor, A is the cross-sectional area, and N represents the number of turns of conducting wire, where mu is the permeability of the core. From equation 2, we can infer the following information: that inductance can be increased by increasing the number of turns of coil, the core element must be of high permeability, increasing the cross-sectional area, or reducing the length of the coil. Like capacitors, inductors are also commercially available with different values and types. Typically, the available inductors have inductance value ranging from few microhenry, which are commonly used in communication system, to tens of henry, which are mostly applicable in power systems. Inductors are also available of fixed value and of variable type, and the core may be made of iron, steel, plastic, or air. The terms coil and choke are also used for inductors, and figure 2 represents common inductors. The figure 3 represents circuit symbol for inductors most commonly used, where figure A is used for air core, figure B is for iron core, and figure 3 is for variable iron core inductor. and here also the passive sign convention is used. For the voltage-current relation expressed in equation 1, a graph is plotted in figure 4, which represents a linear voltage-current relation for an inductor. And this graph shows that inductance is independent of the current, and such an inductor is known as linear inductor. And for nonlinear inductor, the graph shown in figure 4 will not be a straight line, because in that case inductance will vary with the current, and we will assume linear inductors. Now by rearranging and integrating the equation 1, we will obtain a current voltage relation for an inductor. In this, current will be equal to 1 over inductance of inductor, and integrating the voltage across inductor from past time to present time t, or current will be equal to 1 over inductance of inductor and integrating the voltage across inductor from time t0 to the time t and adding the initial value of current in inductor. And this will be equation 2. Here I of t0 represent current stored in inductor from time minus infinity to time t0, and also I of minus infinity equals 0, which represents that no current was flowing through inductor earlier. The idea of making I of minus infinity equals 0 is practical and reasonable because there must be a time in the past when there was no current in the inductor. Now the power delivered to inductor is equal to the product of voltage across inductor and current flowing through an inductor, or it will be equal to inductance of inductor product with current flowing through inductor and rate of change of current. An inductor is designed to store energy in its magnetic field, and this energy stored in the inductor is integral of power and will be equal to inductance of inductor product with integrating the current flowing through inductor with rate of change of current from past time to present time t. Rearranging and performing integration with the result that I of minus infinity equals 0, so the energy stored will be equal to half inductance of inductor multiplied by current passing through inductor square. Now we will study important properties of inductor. First property is that an inductor acts like a short circuit for DC. From equation 1 we know that voltage across inductor is directly proportional to rate of change of current. If DC source is applied, then rate of change of current will be equal to 0. So voltage will also be equal to 0. And in case of short circuit, we have voltage equal to 0. So therefore, an inductor acts like a short circuit for DC, or when a constant current is applied. Second property of inductor is that the current flowing through an inductor cannot change instantaneously. An important property of inductor is that it opposes the change in current flowing through it. Now from equation 1 we know that a discontinuous change in current passing through an inductor will require an infinite voltage, which practically is not possible. So the inductor opposes an abrupt change in the current flowing through it. Or for example, the current through an inductor may take the form shown in the figure 5a. Whereas the current cannot take the form shown in the 5b in real life situation due to discontinuities. However, the voltage across inductor can change abruptly. Like the ideal capacitor, the ideal inductor also doesn't dissipate the energy. The energy stored in it can be retrieved later, and the inductor takes power from the circuit while storing it and delivers power to the circuit when returning the previously stored energy, and at this time it is in discharging mode. Fourth property of an inductor is a practical non-ideal inductor has a significant resistive component as shown in the figure 6. This is due to the fact that an inductor is made up of a conducting material such as copper, which has some resistance, and this resistance is known as a winding resistance and is represented by Rw, and this winding resistance appear in series with inductance of the inductor. You can see from the figure 6. The presence of winding resistance make it both energy storage and energy dissipation device, since winding resistance is very small and is usually ignored in the most of the cases. The non-ideal inductor also have a winding capacitance due to the capacitive coupling between the conducting coils, where the winding capacitance is very small and it is also ignored in the most of the cases except the high frequencies. And here we will assume ideal inductors. Now in this example you have to find voltage across the inductor and energy stored in it, where the inductor have inductance of 0.1 Henry, where the current passing through an inductor is product of 10 with current time t with exponential of minus 5t amperes. Now in solution we know that inductance is equal to 0.1 Henry and the voltage across inductor is a product of inductance of inductor and rate of change of current. So substituting the values, the voltage across an inductor will be equal to exponential of minus 5t product with 1 minus 5t volts, and the energy stored will be equal to half inductance of inductor multiplied by square of the current passing through the inductor. Again substituting the values, we will have the energy stored in an inductor will be equal to 5t square exponential of minus 10t joules. Now in the next example, for the circuit given in the figure 7 under DC condition, in first part you have to find current I, voltage across capacitor and current flowing through the inductor, and in second part you have to find energy stored in capacitor and inductor. Now to start the solution under DC condition, we will replace our capacitor by an open circuit and an inductor by an short circuit as shown in the figure 7b. Now from 7b we know that no current flows through 4 ohm resistor, so the current I and current through inductor both are equal and their value will be voltage divided by total resistance of the circuit, and total resistance will be of 1 plus 5 ohms. So the current I or the inductive current both will be equal to 2 amperes. Now as the capacitor acts as the open circuit for DC voltage, so no current will flow through 4 ohm resistor, and hence the voltage Vc will be equal to the voltage across a 5 ohm resistor and will be equal to 5I, and Vc will have a value of 10 volts. Now for second part, the energy stored in a capacitor is equal to half capacitance of capacitor multiplied by voltage across a capacitor square. Now substituting the values, the energy stored in a capacitor will be of 50 joules. Now the energy stored in an inductor will be equal to half inductance of inductor multiplied by the current flowing through inductor square. Substituting the values, again we will have an energy of 4 joules stored in an inductor. And thanks for watching this video.